All right, so let's go ahead and get started again. For those who want to follow along, have you gotten logged in, set up, or on this page? And so that's under projects, and did you click on the start? So you should get to somewhere like this. Anybody get to here? All right. So, okay. So, for those of you not familiar with our studio, it's the basic interface to type and run code. Right there in the box is the file navigator, and you can click on okay, that's not the right name for it. Let me see what it's called. It should be called 2019-0212 long CI tutorial.rmd. You find that should be the second one on the list. Okay, you open it up. The code appears in the top left corner here. And here. And then you just scroll on down to line 700, and that's where the code for the next little bit starts. So if you're very adventurous, you can try to replicate it and type it in, or just hit the play button, and that'll run that little bit of code. Does the same thing. If not, you can just follow along with the lecture and don't worry about it at all. All right, so let's take a look. First case study. It's a very simple one, not actually longitudinal, but a nice example about how to use the standardization approach by G-formula. So let's consider a question of quitting smoking on body weight change. What we talked about earlier is that some people actually do smoke to reduce appetite, reduce body weight. So it's possible that quitting causes body weight to increase. So a question might be, for those who are smokers, what is the effect of quitting smoking in a population, and so this is in the US setting, on the risk of weight gain? And why it's this particular time window is because we're taking data from, this is an example from the causal inference book, taking data from the NHEFS, the National Health Examination Nutrition Survey. So it's a US population-wide survey on health behaviors, health and healthy behaviors. And this particular epidemiologic follow-up study looks at some people in this particular time window between 1971 and 1982. So it's the effect of quitting smoking in a population of smokers on the risk of weight gain. Why? So why, weight gain being a dichotomous variable. So say we want to try to answer this question using this particular data set. For example purposes, we'll do some simplifications here. So let's assume that this diagram on the bottom is the true representation of the causal relationships and how we can estimate the effect of quitting smoking on weight gain. And the only confounders in that vector C that are important are the ones listed there. So demographic ones, sex, age, race, income, marital status, schooling, and then some behavioral ones, physical activity, and some health conditions or health history. All right, so let's just say that this is the correct causal structure and we have all of the confounders that are able to answer that question. Also that we have complete data, which is usually not true. All of the C are measured prior to A, meaning that they're true confounders. They aren't potentially affected by A. And that this particular relationship between quitting smoking and the probability of weight gain is the one that we're interested in. All right, so first step, we will, let me get to the right place. Load the data, which follow along as well to make sure that it is correct. So we read the data, and we see we have 1,746 people. We'll tidy up the data a little bit by just selecting the variables that we want. Create a binary indicator variable. So this is the weight change, the total weight change between these two time points. Just say if it's greater than 0, we make a binary indicator variable for that. And right here we do something that we should not do in regular data analysis, but for this example we will, which is drop all the observations that have missing data. It turns out actually it's not too many. So we should end up with a, let me reiterate that this is really important. Complete case analysis where we just drop the data from people we don't have measured covariates on is not something we should do in practice. I'll come back to this point later on, but this is just for the example. So we end up dropping about 300 people. You should have in your data set 1476 left. All right, so we have our data set. And then we'll also, to make it easier to estimate, just collapse some of these variables. So age, we'll turn it from a continuous age into whether or not it's more than the median age as a dichotomous variable. Just again, for ease of estimation in this point. We're turning some of these variables into binary variables. All right, so the next thing that we want to do is describe some of our variables. This is basic sort of data analysis tools that we want to do. We want to look at the distributions of our variables, make sure that they make sense. Our binary variables only have two values. The distribution of the continuous variables that we have makes sense, are not out of range, and look at some basic descriptives. So, all right, we look in our data right here. What do we have? So we have our smoking variable. Quit smoking, yes or no? So 0 is no, 1 is yes. Whether or not there was weight gain, so I just tabulated here. So amongst no, let's see if that's right. Yeah, 724, so 65% did not amongst the no, 74% did amongst the quit. So a greater proportion, just in terms of the raw tabulation, had gained weight after quitting smoking, which is sort of what we would expect if our hypothesis is that quitting smoking would increase it. All right, so that's the basic descriptors of it. What we want to do is estimate a causal quantity, which is what is the effect of actual quitting. This might be, so here is the mean, so basically the proportion of people who gain weight from quitting minus the proportion who didn't. So how do we get to this particular causal question of interest? The DIAG that we showed before, the causal diagram that we showed before, shows this very simple relationship. A to Y, C confounds A to Y. So the equations, the dependencies that represent that are Y is a function of an error term, the effect of A and the effect of C. A is only dependent on C, and we can represent this by expectation or a probability. For A, we're specifically interested in the probability of A, so it's equal to so expert is just the exponentiation of the log. So if we estimate this by a logistic regression, to turn that into the probability, we apply the expert function. So expert of an error term plus the effect of C. So these equations right here is how we connect that causal diagram to what we observe in the data, meaning that Y is conditional on A and C, and A is just conditional on C. So far, so good? All right. So that gives us the conditional probabilities and means, and we use our assumptions about exchangeability, consistency, positivity to change the mean sum of Y given A and C times the probability of A given C times the probability of C into an expression about the potential outcomes. And we do that by saying that we can set A, knowing C, we're able to set A and observe directly what the potential outcome given A is when setting A to that value. And so we can use that to estimate given C what this is, so plugging 1 here, and then what this is, plugging 0 here. So that's what we'll try to do. So the first step, fit the models for A, which is a logistic regression model of the probability of smoking, quitting smoking, on the covariates, the confounders, the set of C that we said was sufficient to control confounding. So we fit that model. And I didn't put the output there, but you can look for yourself. You can run the models and take a look at the output. And is what you would expect from a logistic regression model. So one thing that you can do when you're running these is to take a look at the basic regression models for these different outcomes and just make sure on face value whether or not the coefficients go in the direction that you would expect to. So if you ran this, for example, you would see that schooling is positively associated with quitting smoking. The amount of smoking intensity is negatively associated with quitting smoking. So these are things that you would intuitively sort of understand to be true. So this gives some face validity to the models that you're doing, whether or not you're doing them correctly. The caution is I wouldn't overinterpret them because all of this particular model, for example, for A, includes all of these variables, and each one of these parameters that you would estimate, for example, that are here, are interpretable only as this, the association between this and the probability of smoking conditional on everything else. And so on for this. This is this, conditional on everything else. And some of those conditional relationships may not make sense because each one of those relationships has their own sort of causal relationship. So it is possible that these different things mediate the associations between the two. It takes a lot more. Each one of those you can imagine to be a separate causal question. But just in general, to check the associations and correlations between the variables, you can take a quick look at it, but you shouldn't overinterpret it. Okay, so we fit a model for A according to our causal diagram. We fit a model for Y according to our causal diagram. And then what do? So we estimate this through simulation by resampling, by Monte Carlo sampling. So what we do here, we've just resampled 10,000 from our baseline data. So taking all the covariates, we create a random sampling number for them, and then we draw a sample set. And we see it's 10,000. So this is 10,000 samples from our original data with resampling, meaning each person can be sampled more than once. All right, this is a basic principle of Monte Carlo sampling. So what we want to do is draw a large enough sample so that when we put these samples through the simulation, through the different relationships in the equation, we can come up with a consistent estimate of what the parameter should be. So it has to be large to avoid sampling error. And I know there are some rules of thumb, some guidelines about it. I don't know about this particular setting in terms of implementing the G formula. But in general, you want some sample to be at least as large as your original sample size. And probably some factor greater than that. And it will depend on basically how many different covariates you have in there, what you think the different relationships are. But probably practically, you want it to be as large as you can to estimate in your sample without taking too much time. So it's not a great rule, but there are not really any hard and fast rules. So here we've chosen 10,000, which is more than 10 times the original sample. And what we're doing is we're going to take that resample, again, of all the baseline values, and set all of the smoking status to 0, or to blank. We're going to fill those exposure status in. And how we're going to do that, how we're going to fill in the exposure status in the resampled one, is by predicting the probability of example given that model that we had. That model based on covariates, we predict the model A, and set it to this variable here as an intermediate step. And as a check to see whether or not we did a good job with fitting that model, we can compare that to the observed one. So you'll see that using our model to predictive probability exposure, we get about 24.5%, and the actual observed in our data set is 24.5%. So we did a pretty good job. Okay. In order to run it to the simulation, so the prediction model gives you, for each person, a value between 0 and 1. It doesn't give them actually a value of whether or not they were exposed. The values are not 0 or 1. So in order to turn that probability into a 0 or 1, the way to do it is to generate a random distribution, a uniform distribution of numbers between 0 and 1. Take that vector and compare it to the predicted probability. And if the predicted probability is greater than that random value, then you set it to 1. And what that does is that gives you a distribution of zeros and ones that's equal to the mean probability. So doing this, generate a random distribution, and then we compare it to our predicted probabilities and turn that into a new data set. And you can see in that new data set, we get zeros and ones. Rather than each person having a probability, each person has actually a 0 or 1 assigned. And we see that even with 10,000 sample size, we don't actually get exactly to the exact prevalence, but it's close enough. So we get the prevalence here to be 25%. And so the reason that we're doing this is we're basically doing a preliminary step to check to see whether or not the parametric models that we have to simulate these outcomes can at least approximate what we have observed in the actual data. So we'll take that predicted value for the exposure status and put that into our model for the outcome to find a predicted mean value. So then we take the mean of that. We take the predicted outcome, predicted amount, and take the mean of that. And we can see that from our predictions, setting the A from a random draw based on our confounders, and then setting Y based on the predicted value for A, we get 67.3% total gain weight, and that's the observed mean. So we did a pretty good job of approximating, even with our parametric models, what the distribution should be, given our particular causal structure that we had assumed. So I'll just say that this is really neither necessary nor sufficient to show that your model is correct. There's no way to show that the model is correct, because for two reasons. One is that even if this is a biased estimate of the observed distribution, it can produce an unbiased estimate of the risk differences. Say if they're both biased in the same direction, you still end up with a good distribution. Second of all, you could have a good estimate of the observed distribution or the observed outcome measures and still have an incorrect model, because under different manipulations, you could still not have the actual correct estimate. However, if you do this model and you do see that it varies wildly from the observed distribution, then it sort of reminds you to go back and check to see whether or not those models that you've built, those conditional models, are good. Okay, so this is basically the setup and the diagnostic part of it. So what do we do to actually estimate the contrast that we're interested in? Well, it's quite simple. Rather than setting it to the predicted distribution, you just take the model, you force it to be 1, the treatment status to be 1, so quitting smoking. You predict the the mean outcome, the mean proportion of weight gain under that model. You do the same thing again by setting it to 0, get the mean there, and then to get a risk difference. So then you estimate the proportion of people who gain weight under one treatment, then the proportion of people who gain weight under the other treatment, then you find the risk difference, and you see that 11.4%, or 11 out of 100 people are predicted to basically to gain weight. So the causal effect, we'll get to that in a second. Among people who quit, the risk for weight gain is 11% higher, or you can take a risk ratio, just take the same thing, take the ratio, 18% higher risk. All right, so we have these two numbers. So then can we interpret this as a causal effect of quitting smoking on risk of weight gain? This is basically where the justification from prior knowledge and from our knowledge of the causal structures makes sense to evaluate whether or not it makes sense. So a consistency question. Will different ways of quitting smoking, which what we actually observe, lead to different effects on probability of weight gain? This is a judgment call. I don't have one reason to say one way or the other. But presumably, since we've narrowed it down to, a particular group of people, a particular group of time, the closer we can narrow it down to that group of people, that group of time, and to know about the different ways or modes by which they could get to quit smoking, so they can get to us observing them having quit smoking, we can make a claim probably that all of those ways may have a similar effect on the risk of weight gain, conditional on these other factors that we looked at. So for example, if it's physical activity, since we conditioned on physical activity or evenly distributed among those two, then conditional on those factors, does the quitting of smoking have a consistent effect on the outcome? These are things that can't be justified by the statistical model, by the parameters. They have to be justified by our knowledge of the underlying condition, the underlying data generating mechanism. Correct model specification and exchangeability. Did we include all the possible confounders? We included quite a bit of them. But one thing that we might consider is because for this model we dichotomized all the variables, it is possible that there's residual confounding. So you consider a different model where we don't do that. Whether or not there's interaction between different factors in confounding or between the exposure and confounder. We might, for example, think that there are different strata where this effect actually differs. So one thing we haven't talked about before, hopefully you talked about last time, is one important thing in order to be able to estimate an actual, to do a good job estimating the potential outcomes, we have to ensure that there is no interference, meaning that assigning one person to a treatment doesn't affect the effect or the treatment status of anyone else. If you think about it, we don't incorporate any of that sort of information into our models for either the risk of the outcome or for the exposure. Meaning that, say that if we change the value for one person in our study, it may change the likelihood of exposure for someone else. It may change the outcome. So say, for example, if more and more people in a particular group quit, it may be more likely that others quit, or it may be likely that they take on other behaviors that would change the risk of weight gain, and we haven't modeled any of that in this particular setup. I think for this case, since this is coming from a data set where people are very far removed in time, in location, they're sort of scattered all over the place, you can make a general assumption that probably changing the exposure level for one person doesn't affect anybody else in our sample. But this may not be true if you're doing it in like a community setting. In that case, you'd have to incorporate some information about that. Some information about how this can change the distribution of potential outcomes for other people in the study. There are also other ways to model it, but you can also sort of think about it in incorporating it in your outcome model. Here we assume that basically changing that exposure level doesn't affect anybody else. Positivity. So positivity, again, is whether or not we have data support to be able to properly model the probability of exposure, for example, across all of the distribution of confounders. Because if you think about it, if we have one very important confounder and we have no idea about whether or not the person is likely to be exposed in that group, that means we haven't sufficiently controlled confounding for that particular exposure, for that particular confounder variable. We haven't taken it well into account. Positivity is the only thing that we really can check or have any idea of taking a look at with the data. One way to do it is if you have dichotomous variables, you can just look at the proportion of people that are exposed across the different strata of that. And we certainly could do it with some of our confounders, but since we have so many, a more sort of succinct approach is to look at the predicted probability that we have actually calculated already, given all of the confounders we've included. And so that's what we do here, stratified by treatment status. So A is equal to 0, A is equal to 1 are these two different ones. And so the predicted probability of exposure, conditional on all the different confounders, basically helps you summarize whether or not there are any sets of confounders or combinations of confounders that makes it either very likely that they're exposed, so basically deterministically sets their exposure status, in which case the probability would be very close to 1, or very unlikely. Given this particular set of confounders, it's very unlikely that they have that outcome, in which it would be very tiny and close to 0. And we actually see that we have a pretty good distribution of these predicted probabilities in both those groups, and there's good overlap too, which means in summary, the distribution of confounders or the distribution of probabilities is quite similar between the two groups. It makes it a better to do a valid comparison. All right, so positivity is the only one that we can actually hope to verify in our data, because we can actually look at the probability exposures or the distribution of exposures underneath these different covariates. All right, so we're happy with our point estimates of 11% risk difference or a 18% higher in the risk ratio. How do we put some variability? How do we put the uncertainty into this estimate? So because we resampled, we don't have a good distribution that we can look at, so the really only way to get the standard errors in the confidence interval is to bootstrap this process. And so you'll see here that we will take 100 bootstrap samples, and in each one of those, we have to resample with replacement, refit the statistical model, so the model for Y. We don't have to refit A because we're setting A, so we know that deterministically, but we need to refit the model Y in each one of those resampled data sets, run the actual Monte Carlo resampling, identify the estimate from there, right? Either the risk difference or the risk ratio or both. That's what we're doing here. So we bootstrap a data set. We estimate the outcome model Y. We then take a Monte Carlo resample of 10,000. We run it through like we did before, predicting the outcome, setting it to 1, setting it to 0, and then calculate that, and then build a list, build a list of all these parameter estimates. And then after doing that, basically because the standard deviation of that is the error in the mean for that set, we just use that as the standard error and apply the critical value, assuming a normal distribution of the estimate, and we can form the confidence interval. You take that as a standard error, and then you can use that to form the confidence intervals for the point estimates. So gives us the bootstrap estimation gives us the bootstrap estimator gives us the normal based confidence intervals here for the. That's not right. Let me see if I can run it. Looks wrong for the. Looks wrong for the risk difference. Okay, I don't know why this is automatically generated, but it should be 20.5. So the confidence interval for that estimate of 11.3, this is the point estimate. It should be 2.5 to 20.3. And then for the risk ratio, this is correct, 1.1 to 1.25. All right, so that's a basic implementation. Does it sort of follow from what we discussed before? Take our causal diagram, put the implied causal dependencies into parametric equations, simulate using setting exposure to 1 and 0, and then finding a uncertainty estimate for it. Okay? All right. So moving on to a second case study. This is similar to what I've shown before. So for the previous example, it's a very simple confounding structure. There's no real need to actually have used the G formula because there's not that complex longitudinal relationship. Here we do. Here we're trying to estimate in a randomized trial. So you see that this is set. There's no confounding here because it's a randomized trial of ART treatment, which is a treatment for HIV at time is equal to 0. Here is a prognostic factor, or a factor that may affect treatment later. Here it's a viral load greater than 200 copies. Just prior to this treatment time at time t equals 1. And this factor here is affected by earlier treatment and may determine whether or not this treatment, the probability of treatment at this particular time. And then this outcome Y, CD4 counts higher is better. It's a measure of it's a T cell count measure of immune function. U is some unmeasured health status. So like we talked about before, we can estimate this by conditioning on these two. We can estimate this without conditioning on anything, but joint treatment here may be biased because of this feedback here, this time-varying confounder here. So let's see how we estimate the joint effect in this particular population. So we created a hypothetical data set here with 100,000 subjects. Here are the different possible binary treatment values and covariate values. And here's the mean of this outcome, the CD4 count in the outcome. And then here's the number of people with each one. So it's very similar to the setup of the earlier example. So we want to estimate treatment equals 1 at time both t equals 0 and t equals 1. So the joint effective treatment here and treatment here on the CD4 count at Y. Given this, if we assume that this DAG is correct, we can write out these models. So the mean of Y is dependent on A1, Z1, A0. The probability of treatment at A1 is determined by Z1. You see that there's no arrow directly from this treatment to here. The treatment decision, if it makes sense, is determined by that health status. It's not determined by whether or not they were treated before. Right? So treatment is only determined by this. The health status at this point is determined by this treatment here, shown by this arrow. This is deterministic because we've assigned it in a trial. So it's only related to the baseline probability of assignment. All right, so these models are a direct representation of what we have assumed in our causal diagram. So we take the representation of the total probability, and by the causal assumptions, we can replace them. They replace the assignments with the weighted probability of, the weighted mean of Y, given the assignment of A, given the observed value of Z, given the assigned value at A equals 0, times that probability of that variable at A0 equals So just like our previous example, right? So it's our previous weighting example where this helps us determine the weighting to use for the total mean. So if you get to this part with your question, your causal diagram, and your equations, that's the hardest part, because defining how to get that estimate is the hardest part, and then after that you just plug in your data and try to figure it out. So, all right, so in this case we're going to create this sample data set from that table. And you see that we've sampled 100,000 population, and because it's a simulated trial, we've initially treated half the population. So half the population at T0 is treated 1, so A0 equals 1, half is A0 equals A0 equals 1, half is A0 equals 0. And we observe the mean CD4 count in this population, just weighted by the observations, to be 125, which is actually quite low. All right, so what we do, according to the models we had before, we fit either a logistic or a linear regression model to represent each of the probabilities. Treatment at A, this is deterministic, so it's just the observed probability. Z1 is determined by A0. A1 is determined by Z1 only. Y is determined by all of the arrows going into it, A1, Z1, A0. And because we're trying to predict the mean, we're doing it by a linear regression. All the other ones are by a logit. All right, so we fitted the models. We have our model, we fit them. And then we want to do that diagnostic that I said before. Estimate what the mean outcome value is under the observed values, just as a sanity check. So what do? We predict the probability of P of A0. And we predict then, because it comes first, then we predict the probability of Z1 given the predicted model for A0. And then we fit A1 given the model for Z1. Finally, we predict the mean outcome given A0, Z1, A1. Okay, we're in a good shape. We observe 50%. This predicted value gives us 50%. So that just follows because that's how we modeled it. And then we simulate this mean following these steps, given this initial treatment probability. And we get 125.1, pretty close to the sample mean. So we did a good job fitting the data to the observed. Okay so far? All right, so then we go ahead and estimate the contrast that we want to. So we set A0 equal to 1. We predict Z1, setting A0 to 1. And then we predict Y1. Because remember, we don't need to predict A1 anymore. We're going to set it to 1. We predict Y1, setting A0 to 1, Z1 to the predicted value, and then A1 to 1. And we find the mean. And we get the mean here, 150. I forgot to mention ahead of time that by design, from the simulated data, we know for a fact that the total effect is increase of 50 cells per milliliter, and that at each time point it's equal to 25 cells per milliliter. So I know that as a quantity in advance. So this is according to what I expect. And then we can look at setting it to 0, 0, do the same thing. Set A0 to 0, set them both to 0 with the observed or with the predicted probability of Z1, model that mean, get 100, and we get the total difference to be 50 cells per milliliter or 25 per treatment per time point. All right, and this would be a causal effect of that particular treatment if our model's correct, if the assumptions hold about treatment. Okay, so in the previous example, we didn't need to use these methods. In this one, I have made the claim that we do. So let's look at what would happen if we had just done the standard approach of the conditional regressions. So we know that we're estimating the effect at A1. We can do it by conditioning on A0, on Z1, because it's the only thing that goes into Z1, and it effectively blocks the path, the backdoor path. So if we model Y on A1 and Z1, we get that the parameter here is 25. So that's correct. So for A1, we're okay. We've conditioned on the thing. We blocked the backdoor pathway. Through Z1, we've gotten this. We do the same thing for A0. Remember that we don't have to condition on anything. There's no backdoor path from A0 to Y. We do that, model Y on A0, we get 27.1. So it overestimates the true effect of A0 alone. But why? So it's 27 rather than 25. And the reason is because we haven't accounted for the treatment ahead of it, which has its own causal effect, we're in essence rolling in some of the effect of treatment at T1, some of the treatment effect of A0, which is caused by the fact that A0 changes Z1, which changes the treatment probability. So the 27 is not incorrect, but it rolls in basically the effect of A0 alone on Y, plus the effect of A0 on Y through A1. So that's fine. That's the total effect of A0 if we hadn't considered A1. But what we're interested in is the specific effect of if we would to assign people to make sure that they took treatment at A0 and A1. And if we do that and we sum these two, 27 plus 25, we get the wrong answer. We get basically an effect that's higher than the true effect. And that's because you've doubly accounted for the treatment pathway through A1. All right? Okay. Last case study, and this will be the sort of most complex one, and I think this is basically to the extent that I think that most will apply the G formula to try to answer. So just a little bit of review for those who aren't familiar with randomized trials. So the randomized trial it was designed prior to this being formalized, but now, in retrospect, we can see it as a way of trying our best to have a situation where we can observe a distribution of potential outcomes with or without treatment. And the randomization process basically creates, hopefully, a group of people that are similar in every way, both measured and unmeasured, so that assigning a treatment, we know that had we not assigned that treatment, the untreated or control arm can faithfully represent that group under that counterfactual. That works if, for example, the treatment assignment ensures that everybody takes the treatment and ensures that doesn't change. Everyone is followed up consistently. There's no crossover. There's no lack of compliance, which basically never happens in practice. But in any case, the randomization process is sort of the most important process, which is why it's recommended to do an ITT, or an intention to treat analysis, which basically says regardless of what happens after the randomization, we just compare the groups that were randomized to a treatment versus groups that don't. Because that, at the very least, ensures that, at least in some point in time, there are reasonable counterfactuals for one another. So where that falls apart is that if there's non-compliance and that non-compliance differs by treatment. So say a treatment is very invasive or has a lot of side effects, and it ends up being that nobody actually takes the treatment, right? On its face, that estimate, even that ITT estimate, is not a very good one because you've had no real representation of the actual treatment that you're interested in studying, right? That nobody is actually taking that treatment, so how can you estimate that effect? So the less severe example is if there is some sort of deviation either in loss to follow-up, or say the treatment causes some side effects that gets people to stop taking the drug. Is there a way for us to recover the per protocol effects. Per protocol meaning if they had taken the treatment as they were supposed to when they were assigned to it. So for example, you're asked to take 3 pills a day of this particular drug, and you actually take 3 pills a day. Is there a way to try to get to that estimate knowing that all of these other things happen? So the naive way of doing it that was done in the past is to just look at all those people who did follow the rules and just analyze it for those people versus all those people who didn't follow the rules. And if you can think about that, that's basically just the stratification approach that we were showing earlier, which is biased. Why? Because those people who tend to comply may be healthier than the ones who don't comply, whereas that sort of selection doesn't happen in the placebo arm. So we're doing this post-randomization stratification, which we showed earlier, which is not the right way to do it. But there is an analog for the time-varying treatment, which is what basically we're showing we can do with the G formula, which is to simulate if we can make a good claim about the potential outcome distribution being similar amongst those who are either lost to follow-up or non-compliant and those who were conditional on their exposure histories. So let's take a look at how that would look like. So this is drawn from a randomized trial of aspirin in couples that were having trouble conceiving. So it's a multi-center block randomized double-blind trial of aspirin, acetylsalicylic acid, versus placebo in women between 18 and 40 years old with 1 or 2 prior pregnancy losses. So these are ones who have already had trouble conceiving or having a live birth. And the treatment specifically was basically a baby aspirin plus folic acid once a day. The actual people who are randomized to these is slightly different, but for the example data set, this is what it looks like. 81 milligrams of aspirin in the treatment arm given to 614 people, and then in the control arm is folic acid only. All right, it's a basic study set up for this study. Other things that happened in the study was once they were enrolled in the study, they were allowed up to 6 cycles to conceive. And if they weren't able to within the 6 months, basically 6 months, they were lost to follow-up from the study. And then the treatment was asked to be continued through 36 weeks of gestation. The assumption here is that important baseline confounders are age, BMI, the sociodemographic ones, and also study site because it was block randomized, so there are differences between study sites. Factors that may change over time, the things that we're basically interested in controlling the effect of are compliance and also side effects that may come from the taking of treatment, including vaginal bleeding and gastrointestinal symptoms, so stomach upset, nausea, vomiting, those sorts of things. And also the time it takes to get pregnant. The outcomes that were of interest in this trial were live birth, of course, but also any other end of the study. So live birth or pregnancy loss or a potential loss to follow-up or censorship. So the question of interest here is, what is the effect of continual treatment by aspirin? So the per protocol effect. You get randomized to this, you continue to treat amongst this target population if we could retain compliance on through the end of follow-up. So the end of follow-up doesn't necessarily have to mean live birth. It could also mean pregnancy loss or loss to follow-up. So as long as you stay on the treatment for as long as they're being followed up, what is the effect of treatment on this particular outcome, live birth? All right, so in your data set or in your file, I've taken some shortcuts where the actual estimation part is put in a different file. I'll show you in a second. But you should still be able to follow up with these steps. So we read in the data from this trial. It's a modified data set based on this trial. We take a look at what this looks like. There is the subject, covariates, and it's a long data set. So there, for each individual, there are multiple observations at one for each month that they're observed. Whether or not, so these are the covariates, whether or not they were indicators for whether or not they were compliant in that given month, whether or not they were on treatment, whether or not they were assigned to the treatment arm originally, side effects, time varying factors, and then the outcomes, pregnancy, loss, live birth. And this is the indicator if this is the last time that they were observed. Just to describe it a little, see here that there are 614 in each treatment arm. The proportion of live births in the treatment arm is slightly higher, 50% versus 48, 55 versus 49%. The loss is about the same. The censorship is slightly higher. So let's take a look at it. The main motivation here is if compliance or censorship differs between the treatment arms. Because if it's the same, we don't really have a problem. We just estimate it as normal. And this is a plot of basic compliance. I've cut it off to fit it on the page, but here's 60%, 100% compliance. And you can see that the compliance actually for the placebo, for whatever reason, could be random. We don't really know the reason why. Is slightly lower in the treatment arm earlier on. It's quite similar. And then these are the months since the randomization. And then slightly higher in this arm, potentially because more and more live births are happening here. So then the denominator sort of changes in this area. Anyway, there is some indication that there could be a difference in compliance between the treatment arms. So an indication that we might want to apply these methods to try to look at the per protocol effect. So this situation is a bit more complicated than the earlier one, because we have multiple time varying factors that may be related, and they may be sequentially dependent in time. So we have to make some decisions about, if we're doing this modeling, what's the order in which we think these events happen, and what's the order in which we think that they influence each other. I won't go into too much detail. I just want to show the decisions for this particular analysis, the decisions that were made. So we can imagine in a given time point, here's sort of the sequential order of determination. There might be symptoms. They might change their compliance. It may affect whether or not a conception or withdrawal happens in this time point. And of course, at each given time point, it could be one or the other happens. Neither, in one time point, it can't be both that happen. But in general, this is the sort of ordering we can think of. And of course, you can make justifications that it should be a different order, but this is the way that it was decided by the analysts. And here's a flowchart basically for if we're running this simulation at each given time point, what is the order in which we would simulate these outcomes? So in general, we have baseline confounders plus the time-varying confounders, for example, the symptoms plus compliance of the previous time point. So you can imagine at a certain point in time, it could be that your symptoms in the month before affect how you are complying with the medication this month. Same thing if you So yeah, so if you had symptoms in the months before, it may affect your compliance at the observed time. So X here is the compliance. If you're compliant at this time point, it may affect whether or not you experience symptoms at that time point. The drug, if it has any effect, it may affect, so this whole thing is not a causal diagram. It's just a flow chart for trying to estimate this. So it's not that bleeding causes conception at this time point. It's just that you're following through to then estimate the next stage, which is, okay, compliance may lead to this. Then the next thing we estimate is whether or not a conception of a pregnancy happens at this time point. If it does and they don't stay in, if it doesn't and they stay in, then you go to the next one and you continue to iterate through. It could be, even if no conception happens, they're lost to follow-up, so they could be censored and no pregnancy. Even if conception happens, they could still be lost to follow-up, or there could be a pregnancy loss or a live birth. All right, so that's just the general flow chart for how they think these variables are related to each other in time. So given this order, you do what we've been saying before, is we fit parametric models for each one of those variables. So this one is an example of the probability of compliance at month K. And so I'll come back to this. So we're modeling it by the baseline set of confounders plus the time-varying confounders plus an indicator for the month. So I'll point out some things. So rather than just including the binary variables or just including the continuous variables, they've done a little bit more flexible modeling, which is that maternal age at baseline, its effect on compliance may not be linear. It may change over time. So you might think, for example, if someone is older, their compliance may reduce over time, whereas for somebody who's younger, that compliance may not change. So just some flexible modeling about the relationship between age at baseline and the compliance over time. So similarly, they've also decided that initial BMI may somehow change compliance over time. It may be through symptoms or maybe some other reason. And then also that months since enrollment itself can and does change compliance. Like we know that the longer people are in a trial, the more likely it is that they'll decide they get bored, they don't see the outcomes they want to see, the compliance just goes down as a baseline, regardless of any other characteristics that goes down. So the other thing that they've decided is that your compliance, so the compliance here is the model, from at a given point in time is also related to the compliance and the symptoms, so the GI and the bleeding symptoms from 2 time points before. So this model allows the compliance at one time point to be affected by n-1 and n-2. The one thing that you'll know, which should be obvious by now, is that at a certain time point, the compliance can't be affected by anything that we have designated to be subsequent to that. So compliance at one time point can't be affected by conception or pregnancy loss at that time point, which makes sense. It should only be influenced by things that happened before it. All right, built these models, you take a resample, and you iterate through it. So the one thing that helps increase the efficiency of this simulation is to put in the features of the observational study or the trial that, or the trial that actually are deterministically known to exist. For example, because all of these people that were enrolled in this trial were known to not have been pregnant at the time they enrolled in the study, the earliest it could happen, live birth can happen is 8 or greater months. And actually it was observed in this trial that that's true. There are no pregnancies before 8 months since randomization. Right, because fertilization has to happen then a birth, even if it's preterm. There were no pregnancy losses less than 2 months because of the way that they are, the test for whether or not someone's pregnant, it takes a few weeks. So there were actually no people, there was not really a way of identifying any pregnancy that occurred prior to that. In the data, there are no pregnancies, conceptions that were identified in less than 2 months. So when you're doing these simulations, you can force basically values for a certain iteration. So for the first 8 months or for those 2 months, that particular value has to take, that particular observation has to take on that value. And that basically increases the efficiency that your model fits the actual data. Similarly, everyone, remember that you were allowed 6 cycles. So everyone who has not successfully conceived by 6 months post-randomization are censored. So you can set all of those people to censored if that occurs. And then the follow-up ends at 15 months. And that's the 6 months plus 9 months of, right? So they have to conceive within the first 6 months. And then after that, follow 9 months, 15 months or thereabouts is the maximum amount of time that follow-up can happen for a live birth. All right, skipping all of the details of the actual estimation. If you want to actually run it, it does take some time because they're resampled 500 times 16 time points and then bootstrapped after that. So it does take some computational cycles, which is why I didn't run it here. But you can open up the file, which is in the directory of that, and run it yourself to see. Okay, so what happened? See here that the natural course is slightly different than the observed, about 2% more. It's still fairly good since we fit 8, 9 different parametric models for it. Still simulated the natural course fairly well. And then taking the per protocol estimate, making sure that they take treatment on any time they're still in the study, was found to be 51% here. This is the proportion of live births. And this is the observed proportion. So imagine that basically that because of potential bias in the compliance or loss to follow-up, it could be that people who decide to stop don't have any trouble conceiving. So the estimate from those who remain in the study could be higher than the actual one if we had followed them up over time. 51% live birth here. Under placebo, 45%, and this is the observed one. So the per protocol estimate here is 6.3% greater live births under the treatment. This is actually fairly similar to the ITT one that was actually observed. All right. So, any questions about this before we wrap up? Okay. Yes. Well, well, if you look at the compliance here, right, it's fairly similar. So there's not that much. This is an example. So they didn't actually use it for the actual study. Right, this is just an example to do it. In the actual study, they did report the ITT, and in fact, there was no benefit. So one potential sort of cynical thing is to say, okay, maybe this differential compliance, however small it is, did have a effect on the efficacy, right? So the ITT gives you the effectiveness if there's no loss to follow-up, if you have complete data, generally can give you an estimate of the effectiveness. But, and in this trial, they found basically that within the variability, they didn't find an effect. Even though it was slightly higher in the aspirin group, it was very much potentially due to chance. So they did see some non-compliance. So one way to think about it is, under ideal circumstances, the efficacy estimate. Can we get that efficacy estimate by correcting for these differences in symptoms, compliance, loss to follow-up, right? The one is to get the best possible estimate of that efficacy. Well, it turns out doing that the non-compliance or the difference in non-compliance and the difference in symptoms didn't necessarily make it any more convincing, right? But we don't know unless we try to estimate that. Does that make sense? Yeah. Right, that's always the first analysis, right? The question is, do you have, so in this case, non-compliance is about 30%. It's actually not too terribly bad. So what if you had a trial in which there's either a lot of non-compliance or crossover? So we saw this with some statin drugs, I believe, that basically we showed there was no benefit. But the problem is that it was open label, and then they ended up having like 80% crossover into this new one anyway. So what can you do with that? You take the ITT, you find no benefit. That's because everybody was on the drug, placebo or not. Right? There's nothing you can do with the ITT to help fix that. And the regular ways of getting the per protocol effect are biased. So in that circumstance, you do need to use an alternative approach to try to get the best efficacy estimate if everyone had been compliant. Right? But we don't know prior to, hopefully we don't know prior to running this analysis that it would be similar. Right? We only know after having done this analysis and trying to recover an efficacy, that there wasn't much difference, right? But we wouldn't know before doing it. We'd only have the ITT. So does this approach demonstrate the magic of the approach? No, it doesn't. But it gives you a principled way of trying to get to the per protocol effect. All right, so just to review the sort of standard flow of this, represent the causal structure that you assume to exist. So some of it can be temporal ordering. The temporal ordering can help you do that. Draw that DAG, model the temporal structural relationships that are implied by that. So you'll also see it referred to in the literature as the Q model because of the notation that is used to summarize. The Q model is basically the structural, the system of structural equations that determine the outcome. Resample the baseline values, simulate the outcomes underneath that. Repeat for whatever contrast that you are hoping to get. So I only talked today about static intervention regimes. So the per protocol is making sure that people are assigned to 1 or 0 the entire time. So Vivas on Friday will talk to you about dynamic treatment regimes, which means that at each point in time, the treatment decision not only is determined by, well, the treatment decision can be by some particular formula that is adaptive to, rather than saying that for sure at this point in time somebody's going to be taking the drug, we make it adaptive to the covariates or the health history that has happened before it. So it's an extension of this approach. And then you can bootstrap this to get your standard error estimates. Okay, so what we haven't talked about is missing data, and which is a huge problem. The implementation that you'll usually see is that you will take a single imputation, so by chain equations or whatever, for your for each bootstrap sample. You take that bootstrap sample, and then since it's summarized anyway, you in essence have a multiply imputed set. No interference. So as I said, there are extensions to this where you can take into account the fact that distance to other treated units may have some sort of functional relationship to the distribution of potential outcomes. So that's one way of incorporating that. Other models that do this sort of by default are agent-based models, if you've heard of them, which build this sort of interference into it. One thing that it's important to do, so for each one we showed the system of equations that we thought was to exist, but for certain things, particularly ones that are close in time, we might imagine that we actually aren't correct about the causal ordering, and one of them could precede the other one. In fact, it's likely that these things sort of happen. So one good sensitivity analysis is to see whether or not your estimates differ if you change that system of equations. Rather than L being determined, or A1 being determined by L1 only, maybe that L1 measure you have is actually after A1, or any number of these particular ones you think it might be problematic, to test your final point estimates based on sensitivity to those things. Some of them, if you measured one at month 1 and the other at month 2, there's no way that one determines the other, right? But in other circumstances, it's less clear. Of course, also test sensitivity simulation error, draw a larger sample. In practice, this does seem to play a role. I've done simulations with up to like 1 million, and there's still variation at 2 or 3 decimal points. It is sensitive to simulation error. So as much as computationally possible, try at least with larger ones to see if you have more variation in your outcome. For the natural course, as your diagnostic, you don't necessarily just have to look at the means. You can look at the counts. You can look at medians, distributions, and those are different tests for whether or not you think that you've generated a good outcome distribution from your simulations. So 2 last things to think about. Rather than a standardization approach by the simulation and inputting exposure variable, it's also possible and commonly done to use weights to estimate your parameters from a single regression model. And how that works is, remember the propensity score, that probability of treatment that we estimated before, you turn that into a weight. You take 1 over, well, it's stabilized weight, but in essence, you take 1 over that, and you use that to estimate, to weight each observation you have in your sample. And what that does is you end up basically balancing your propensity scores and having people who are equally likely to be treated. And that contrast between a group of people who are treated and a group of people who aren't treated, in essence, also estimates that contrast. So that's a computationally simpler way of doing it. You take the propensity score, you take 1 over that. And then how to do that sequentially in time is that you have 1 propensity score for each point in time. Probability of treatment at each point in time determined by all of the covariates and exposures beforehand. Do those weights, and you take the product of those weights as your joint summary probability or probability weight for that individual. And then you can turn that into 1 regression model. So you just estimate those propensity scores and run 1 regression model weighted by that. There's computational advantages to it, but the other issue is that it creates a pseudo-weighted population that doesn't really exist in real life, that doesn't have much of an interpretation. It's some group that seems to be balanced on propensity scores over time. It doesn't apply to a real population, whereas in your G computator, in your G formula, you can do this standardization. If your assumptions are correct, then it applies specifically to that population that you have observed with the covariate distribution that you have assigned to them. An extension of the G formula approach called TMLE, or Targeted Maximum Likelihood Based Estimation, changes this in some ways. It brings in, so you have your G computation, and you bring in the probability weighted approach. So the G computation gives you an estimate of the outcome. The inverse probability weighted approach gives you an estimation, a model for your exposure, because it's the probability of exposure. You put them together, and then you also use machine learning approaches to estimate those models. So those regression models that you have, they have a number of covariates, for example. You can use a machine learning approach, cross-validated approach, to help you select the best combination of those variables to more efficiently estimate each one of those equations. So this approach has been shown in certain cases basically to be as unbiased and as efficient as any one of, so say just a generalized linear model or just one other method of estimation. All right, so just some helpful resources. There's some documentation. So G formula is implemented in Stata if you use Stata to do both static and dynamic treatment regimes. I would highly recommend the causal inference book for this and any other issues in causal inference, and it's I think it's quite amazing that it's available for free at the website. It's a nice review paper of this and other methods by Ashley Naimi, who gave some short courses on this, and that's where I got the code examples from. So if you want more details about that, you want more explication of the different examples, I would recommend going to his website also and looking at them there. It's really great stuff, good examples there. So running over on time, but just some last things, some clear thinking, really doing those exercises about, what cause, what contrast are you trying to estimate? Can you define consistent effects of those are really the most important part of it. Then everything after that is sort of just the computation. Dynamic treatment regimes will come later. Any other questions or comments, please feel free to email me. I think the organizers will have my details. That's also a link to my email address. Please, if you have any questions about the topic, about other topics, about the code or presentation, please do email me. And I'll reserve the final word to Judea Pearl, who's sort of a godfather of modern day causal inference, who says, in giving his definition of what causation and causal modeling is, he says that causal model is a set of assumptions about the data generating process which cannot be expressed as properties of the joint distribution of observed variables. So the causal process is everything other than the statistics that go into it. The statistics help us get to that estimate, but we can't give that interpretation without, we can't give it the causal interpretation without all of the other causal assumptions that come with it. And that's, I think, the most important part to recognize, is we can do all the estimations that we want, but without those particular assumptions about causal relationships, how they link, for example, the statistical model to potential outcomes, you can't say anything about causation, and there's no way to get around it. All right. I'm a little bit over time, but I'm happy to take any questions. Yeah. Yes. Can you say a little bit more about that? What are you thinking about? But we can't, because we don't know what the actual distribution of it is. We don't know what the true distribution of it is. We just try to get at it by resampling. Well, I'm not saying that we're not saying specifically that, for example, the distribution of the outcome is normally distributed, right? We have to bootstrap it. I mean, you can, for example, if you're just running the simple outcome regression, then you can just, if you're just looking at the outcome model, then you can take and you believe that the outcome is normally distributed, you can just take the 95% confidence interval from that particular outcome model. But we don't know, given all of our different inputs, what that true distribution should be. I mean, consider that if it's going a little bit outside of this, but if the model is fully deterministic, then it could be that we have no error. It should be 1, right? I don't want to say that the true distribution has I don't want to say that there is some particular distribution to it. Yeah. You could, I think, and that's what I think. That's the work behind the targeted maximal likelihood estimation, where they just try to minimize the loss function, the particular loss function, and derive estimates. That's a bit beyond sort of my knowledge, so you have to look at a little bit of literature and say what's appropriate for that. But yeah, but this particular application, where we're just deriving the estimates from resampling and Bootstrap, then that's the way to do it. But yeah, I think you can. Yeah, so there are, I think there's lots of work and lots of people trying to think of different clever ways of diagnosing omitted variable bias, but at its heart, I don't think that you can. Because there's always an explanation for some observation that you see. And it could be true and it could be the omitted variable. And the determination of that does not come from anything other than prior knowledge. So, or assumptions about the data generating mechanism or design. That's where design comes in, right? That's why we use things like quasi-experimental designs or randomized trials, is because we can sort of give up on making those decisions for ourselves. We'll say, by assumption, there is no omitted variables, but we're still making that assumption. So here's another thing to think about, is even without any omitted variables, and you have a system of equations, and you've observed all of the conditional probabilities and all the distributions between them, you cannot, without additional assumptions, generally figure out what the direction of arrows should be. Right? There's always multiple, in fact, an infinite number of Markov equivalence graphs that show that are equivalent to the observed data. So you have to, by assumption or knowing sort of the temporal order of things, put those arrows in yourself. But they're not generated from the data. There are certain things you can generate from the data, conditional independences and those sorts of things. But in many cases, the direction of the arrows has to be by assumption. Yes? I think if you are trying to ask, so it's nice that you asked that. Okay, so Miguel Hernan, I think this is actually published now, but this is from the archive paper, describes that the process of data science has there's three things that are trying to be done in data science. One of them is, and it's related to what we think about in epidemiology. One of them is just description. There's a proportion of things different between different groups. That's important to us. We need to know it. For example, a burden of disease. We need to describe it, do our best to describe it. Next is prediction, which is a bit of a misnomer because we're not predicting anything in the future. It's all in the past. But can we do our best job in taking all of the input variables and map that into an output? So a lot of machine learning, for example, is just this. Can we best discriminate or classify one particular outcome? This doesn't really have anything to do with the causal process. It could be that they're causally. It could be that there's just enough correlation between these different things that you are reliably able to predict an outcome. The last is causal inference, which by definition, because we're talking about counterfactuals or potential outcomes which we can never observe two of, are always going to require assumptions to link observed data to what may or may not have happened, even a randomized trial. If you're in causal inference, then you should apply some approaches that try to make use of those assumptions and put them into your observed data. So the answer is no, you don't need to use any particular type of method, but the method that you can imagine a randomized trial, an ITT in a randomized trial is an approach to causal inference, and you can estimate that by a t-test. So it has nothing to do with the specific method that you're using, but because of the design, because of our assumptions that compare the two groups, we have, by definition, determined what maps the observed Y to the potential outcome Y, and we've made that determination. If that setting fits for what you're trying to do causal inference with, then fine. You don't need to use any particular method. These particular methods are because we're trying to answer questions about sequential exposures that happen over time, or about some sort of mediating mechanism or pathway, and we need to be able to change a sort of a very complex counterfactual question from our observed data. And we know the pitfalls in the past of just using those plain old regression models to look at that observed data, because it collapses these categories that don't really exist in real life and don't approximate what it would look like under intervention or randomization. Anything else? So if you're logged into it, you should have access to it, to all of the files on the RStudio. If you don't have it or don't want to, I will export a copy of this PDF and give the R Markdown file to the organizers, and you should be able to get them as well. Okay, thanks.